180,000 GitHub stars, millions of downloads. Everyone is showing you how to install it, how to connect WhatsApp, how to make it do tricks. But here's the thing, if you don't understand the architecture, you don't understand the attack surface. And this thing has full access to your machine. Today, I'm breaking down the entire OpenClaw architecture, every layer, every component, and at each layer, I'm going to show you exactly where the security boundaries are and where they break. This is the video I wish existed when I first started digging into this project. So follow along. The first component is gateway. It's a single daemon process on port 18789. Think of it as air traffic control. Every message, tool call, and session flows through this one process. Under the hood, it's a WebSocket API using type frames and JSON schema validation. This isn't just a bridge, it's a full control plane. By default, it's loopback only, but the second you tunnel it through Tailscale or SSH for remote access, you have exposed a remote code execution interface. Slowmist already found hundreds of users with their gateways exposed to the internet. No password, no protection, wide open. To lock this down, use device pairing. Every new device needs approval and a signed challenge. Pro tip, set an odd token. If a connection frame doesn't have it, the socket closes immediately. Second one is channels. Channels are why OpenClaw feels different. It doesn't trap you in a proprietary chat window. It integrates directly with your WhatsApp, Telegram, Discord, Slack, and even iMessage. Architecturally, this is handled by adapters. Whether it's a text message, an image, or a slash command, the adapter standardizes it into an identical structure data before it ever reaches the gateway. The system is smart about session management. DM collapse into one main session while group chat stay isolated. You control the trigger always. But if you saw my first video, you know the catch. Every single message coming through this channel is untrusted input. A single well-crafted prompt injection via WhatsApp can chain through your entire tool stack. In this architecture, your channels are the primary entry point for attacks. After the gateway, the message route to the agent runtime. The standard feature here is the lane queue, one of the smartest architectural choice in this project. It's serial by default with explicit parallel option. Every session gets its own lane, executing tasks one by one to prevent race condition and state corruption. Inside the runtime, prompt engineering is pure mechanical assembly. Model resolver manages multiple providers and automatically hot swaps to a backup if you hit rate limits. System prompt builder merges instruction, tools, skills, and memories into a single prompt. Context manager tracks windows size and triggers compaction to prevent overflow. This drives the agentic loop: intake, assembly, interface, tool execution, and repeat. It cycles until the task is complete and resource limits are hit. You can even run specialized agent like a calendar or code review agent, each with their own workspace and permission. It's clean, but keep in mind, if agents can talk to each other, you have just created a lateral movement path for an attacker. Next one is skills and tool. This is where OpenClaw gets its hands, and from a security perspective, it's terrifying. Take the browser tool. It uses Chrome DevTools protocol to take semantic snapshots of the accessibility tree, which is 90% cheaper on tokens but grant full navigation access. Then there's shell execution. It runs as a child process with critical risk, capable of executing any command or scripts on your host. In a full file system, read write, cron jobs, and even camera access, and the agent literally controls your machine. Then you have ClawHub, a registry of over 3,000 community built skills. These are just folder with a skill MD and some scripts, but the agent can search, install, and even write its own skill on the fly. The skill are your supply chain, and supply chain are targets. Password One security team found malicious skills using stage delivery. It starts with a simple dependency. The agent hits a staging page, runs a decoded command, and pulls down a second stage script. The script downloads a binary and even strips macOS quarantine so Gatekeeper can never scan it. We have seen hundreds of skills distributing info stealing, malware through this exact chain. The fix, sandboxing. You need Docker based isolation, tool allow list, and strict policy controls on incoming DVMs. Running OpenClaw Doctor will flag your risky configs, but most users stick to defaults, and the defaults give the agent full access to everything. Memory is what makes OpenClaw feel alive. It uses two mechanisms: JSON transcript for a line by line audit of every message and a tool call, and a memory.md for distill preference and summaries. Recall is powered by a hybrid search. It combines vector search for semantic matching, like linking login problems to authentication bug. A file monitor auto reindexes everything the moment a file changes. When the context window fills up, compaction kicks in. It's a smart forget approach, summarizing and compressing the conversation instead of a hard cutoff. But here's the risk: these files are plain text on your disk. If an attacker hits your file system, those transcripts are forensic gold for your entire history and behavioral pattern. If you are using OpenClaw, these six are non negotiable. Run OpenClaw Doctor and fix every flag. Set gateway auth, never expose it without a password. Enable Docker Sandbox. Allow list only the tools you actually need. Audit ClawHub skills like any other third party dependency. Use the strongest model possible right now. That's Opus for the best prompt injection resistance. Let's put it all together. A message hits a channel, the adapter normalizes it, and the gateway routes it. The lane queue serializes the execution while the runtime assembles your context, picks a model, and kicks off the loop. The model thinks, calls it tools, and loops until the job is done. The response streams back, and the memory persists. Look, OpenClaw is genuinely impressive engineering piece, but it's running with full host access on machines holding your most sensitive data. In this world, the architecture is the attack surface. Now you understand both. In the upcoming video, I'm taking this a step further and exploiting these boundaries live. We are doing a skill supply chain hack and a sandbox escape and a prompt injection that leads to full shell execution. Subscribe and turn on your notification so you don't miss that. Drop a comment below: which layer do you think is the weakest link? And seriously, if you are running OpenClaw right now, go run OpenClaw Doctor before you do anything else. That's it. I'm UD signing off.